So welcome back. This kind of goes along with both 2.5 and 2.6. 2.6 is more of kind of we've already covered it, go over some experiments with a bouncing ball, do an average. A lot of the things that we've already talked about, recording the data, looking at scatter plots. So we did a lot of that in 2.5. So 2.6 was really an application. But as you go to ALEKS, there's one thing that really isn't covered in any of the lecture material, and I just kind of want to go over it real quick. And it's the concept of this functional notation. So we've already talked about two particular things as we went, and we talked about a linear equation. So a linear equation looked like y is equal to mx plus b, and then example would be something like y is equal to 2x plus 3. This is a linear equation. And the linear just is a straight line. So if I graphed this thing, it's going to be a straight line. Okay, and here's an example of that. And then we looked at this exponential with exponential growth and decay, and that looks something like y is equal to a times b to the x. A was some initial value, and then b was the base, just some general base. And this was 1 plus or minus r is the way we use that. So r was the rate of growth or decay. So if this was 2% a year, this number would be 0.02, the corresponding decimal. And if it was increasing at 2%, so we would multiply this 1.02 to whatever initial value was. And if this was decay by 2%, it would be 1 minus the 0.02, so that would be like 0.98. So each time I'd have 98% of what was left. Okay? So those are two things that we had covered, and it goes back and touches over that again. Finding the line of best fit, scatter plots. We talked about all of those in 2.5. So, but one thing that ALEKS kind of throws out there, and I wanted to make sure that you're comfortable with using this notation, is the functional notation. And functional notation is just this thing, f parentheses x, and for up till now we said this is a multiplication f times x, and we've had to distribute. But this is not a multiplication, it is just a name, okay? It is like Ted, John. So I can have like f of x for Ted and g of x for John. Each one has a particular name. Each one has a particular rule. It could be the same, but in general, this would be different, okay? So the way this is read, it's a couple of different things. It says, f is a function of x, okay? That's very precise when you go into pre-calculus. It just says when I get one value of x, I get exactly one value output. So this is kind of a black box types of concept. I put an x in. I've got some machine in here or mathematical rule, some ordered pair of numbers. And when I run this thing out, I'll get the y value, which is whatever the value is corresponding to your input. So this is the output. And if I graphed it, it would be the xy or the x in a different notation, whatever that value is at that point. And I'll talk about that in just a few minutes. Okay. So for this one, I could call this guy f of x 2x plus 3. Now what it means that the value of this thing all depends on x. F is a function of x. F of x is equal, here's the rule, okay? And that's how they are related. The output to the input. Input to the output is take the input, whatever that number is, multiply it times 2, add 3, or whatever that rule says, okay? So in this case, it just happens to be a linear function, okay? So for this one, it would be f of x is equal to a times b to the x. So one of these, let's call this something a little different. If I'm doing a population growth at 5% a year, this is where this comes into play. This gives me a reminder that, hey, I'm talking about population. And if I'm doing this, and if I'm saying time, I like to use the population as a function of time. And this is what you would see most likely, that P of T is some, let's say, some initial population, some P0 at time 0, and then 1 plus your rate of growth to the T. So you would say, okay, well, I initially had 1,000 people at some place. I had a 5% growth, so this was 1 plus 0.05, 1.05 to the T whatever in years, okay? So this is just a general way of reminding you that, hey, population depends on time. It's not like a fixed thing. It's not like a constant. This thing's going to vary. Here is the rule to calculate it. And then this thing, here's the next step, okay? I would like to tell you to evaluate that rule for a certain value of x. And the way I do that is give you the number here. So f of 2, the value of the function when x is equal to 2, this is the general rule. Here's a particular output when you have 2 as an input. And wherever you see the x, you replace it by the number. So this would be 4 plus 3. That would be your 7. Okay, so f of 2 is equal to 7. So you would plot the point 2, 7, or 2, 7 would be on that graph of that straight line. Okay, but this is using the functional notation. You could do tables. You could say stuff like, here's x, here's my y value, which is a function of x, and the f of x is whatever your rule is, 2x plus 3 in this case. And then you could do different values of x. F of 0, that would be 3. 1, the value of the function at 1, different ways that you'll hear this do the value of the function at 1. F of 1 would be 2 times 1, 2 plus 3. That would be my 5. And then we did the 2 a while ago. So 2, f of 2, the value of the function when x is 2, and that was the 7. Okay. So the very same thing here, once we've got this equation, growing at 5% a year. So I've got the 1 gives me the original amount, the 1,000 or whatever the previous thing is, and then 5% of that. And then the next one and the next one, I keep doing the 1.05. But now if I wanted to evaluate that for P of 5, this says what is the population? The population when T is equal to 5 years. Let's just say evaluate P when T is equal to 5. Well, P of 5 would be 1,000, 1.05. Now, I was talking about T. I'm replacing it with the 5. So evaluate that at 5. And that would be, to the nearest whole number, 1,276. The population would have grown to that. Yeah. So that's the concept of a function, evaluating a function at certain numbers. Just in case you may or may not have seen that before or actually kind of used to it. But that's what all this is about. It's not solving anything. I can't divide out the f. I don't want to split this thing up. This is one name, and it would be like, here's n, and there's the AME or something. You know, you don't want to split that up. That's just one concept. Okay, so I hope you find this helpful. You'll see this thing in Alex, and we'll see you next time.